All right, so this is a demonstration video for the hypothesis testing chapter. And I'm going to use my hypothesis testing worksheet that I've made available to my students. It's not necessary in order to be able to follow along, and you can certainly create one very similar to it for yourself if you so desire. I find it helps guide us through the steps that need to happen. So, researchers have noted a decline in cognitive functioning as people age. However, the results from other research suggest that the antioxidants in foods such as blueberries can reduce and even reverse these age-related declines, at least in laboratory rats. Based on these results, one might theorize that the same antioxidants might also benefit elderly humans. Suppose a researcher is interested in testing this theory. The researcher obtains a sample of n equals 16 adults who are older than 65 and gives each participant a daily dose of blueberry supplement that is very high in antioxidants. After taking the supplement for 6 months, the participants are given a standardized cognitive skills test and produce a mean score of m equals 50.2. For the general population of elderly adults, scores on the test average mu equals 45 and form a normal distribution with a sigma equals to 9. So that's our standard deviation. Can the researcher conclude that the supplement has a significant effect on cognitive skill? Use a two-tailed test with an alpha of 0.05. And then we'll come back and we'll do B, we'll compute the effect size measure. So when we're looking here, even though in laboratory rats, the antioxidants can reduce or even reverse the declines, we're going to use a two-tailed test because humans are not rats, and it could go either direction. It could be that these antioxidants have a similar effect as with rats, so it could decrease them, the decline, or it could be that it has a very different effect and it could increase. So we're going to use a two-tailed test. We're also using a two-tailed test because the prompt tells us to use a two-tailed test. And you can see there that I had already done this more than once. Various shenanigans have ensued in my house. So, hypothesis testing worksheet, step 1, state the hypotheses. We need to know before we state our hypotheses whether we're doing a one or a two-tailed test. And in this case, we're going to use a two-tailed test. And we need the population value for the general population of elderly adults, and that was mu equals 45. So in our alternate research hypothesis, H1, sometimes you'll see it HA, that is mu does not equal 45. And then our HO or our H naught, our null hypothesis, is that the population of elderly adults that do take the supplement is equal to 45, that they are unchanged by having the supplement. Next, we're going to make a prediction. In order to make the prediction, the idea here is we're stating our critical values. We need to know that it's a two-tailed test, and we need our alpha level, which is 0.05. So what we're doing is we're trying to form the boundaries where we go from this is what we expect if the null hypothesis is true, to this is really weird outcomes. They are unlikely to occur if the null hypothesis is true. So in step 3, we're going to actually calculate the Z score. And yes, it's Z. I'm Canadian, so Z. The middle part, this part here, if the score that we calculate falls in this region, we are going to fail to reject the null hypothesis. This is within the realm of what we would expect just by sampling error. In the tails, and we're going to have two tails because it's a two-tailed test. It's a non-directional test. This, if the value we calculate falls in one of these two areas, then we're going to reject the null and accept the alternative. Okay? We need to find these boundaries. That's the task in step 2. We want the area under this curve in both of the tails to sum to our alpha level. So because we have a two-tailed test, we need to take our alpha and divide by 2. So we do 0.05 divided by 2, which is 0.025. So we're looking for a tail that is 0.025 out here, and because it's a symmetrical distribution, 0.025 to our left. And if we add our two tails together, we get our alpha level. And that's why we have to divide by 2, because if we had 0.05 here and 0.05 here, when we add them together, we'd have 0.10, and 0.10 is not the same as 0.05. It's just how math works, right? So our critical values we're going to look for in our unit normal table. We're going to look for a proportion in the tail. That's column C on my, my chart. And I'm going to look down in this column until I find 0.025. And so I scan down here until I find 0.0250, and then I read across to my z-score. And the z-score, you may or may not be able to see it too clearly here. It is 1.96. Okay? So I come back to my diagram, and I absolutely 100% recommend that you draw it out. We have positive 1.96 as our boundary on our right, and negative 1.96 as our boundary on the left. So our critical values are plus or minus 1.96. So now I compute the test statistic. The test statistic, and this is generic, so it prompts statistic to be computed. That is going to be a z-score. And in order to calculate the z-score, I need to calculate my standard error of the mean, which is the standard deviation divided by the square root of n. The standard deviation of the general population was 9, and I had a sample of 16. So I have 9 divided by 4, because the square root of 16 is 4. And 9 divided by 4 is 2.25. And then I calculate my z-score, which is the mean of my sample, subtract mu, divided by my standard error. The mean of the sample was 50.2. The mean of the general population was 45. And then my standard error, this value, which I plugged down here, is 2.25. So 50.2 subtract 45 is 5.2. And I divide by 2.5. Sorry, 2.25. And I get 2.31. So this is the value that I'm going to compare to the cutoff values, the critical values. Okay, so if I redraw that distribution, I had positive 1.96, negative 1.96, right? Those are my cutoff values. The value I calculated is 2.31. So if 0 is here, right, it's 2.31. So this is in one of my critical regions. I am going to reject the null hypothesis. My evidence could be this diagram, or it could be 2.31 is larger than 1.96. It could be that 2.31 falls in the critical region. And then if you reject the null hypothesis, that is the same as saying that it is statistically significant. And so the researcher can conclude that the supplement has a significant effect on cognitive skill. The researcher can conclude that the supplement has a significant effect on cognitive skill. And I'll pause here, I'll come back, and we'll compute Cohen's d.